Okay, so in the previous lectures, we talked about oxidative addition, reductive elimination, transmetallation. I want to finish up with two more, migratory insertion and beta hydride elimination. Let me first discuss migratory insertion. So this is reaction number 4. Okay. And so migratory insertion assumes that you've got your metal complex and you've got these two organic groups, A and B. A being your electrophile and B being your nucleophile. And so as the nucleophile attacks the electrophile and forms a new bond. Please notice the new bond between A and B. Now, having said that, even though B attacks my electrophile, I still am bonded to my metal. Now, common electrophiles are carbon monoxide, alkenes, and alkynes. And I'll show you examples of all of these as electrophiles as we move on through this part of the lecture. Common nucleophiles, anything really with a negative charge. So hydride sources, alkyl, vinyl, or aromatic, negatively charged sources. So let's jump in and start discussing migratory insertion with carbon monoxide. Okay. So let me give you an example. Okay. We already know that alkyl groups are negatively charged systems, right? We have a negative charge of them when we're talking about their electron count and we're trying to figure out the oxidation state on our metal. So we already know that they are our nucleophiles, our negatively charged systems. Not surprisingly, our carbon monoxide is our electrophile. And so just like we had before, let me put this in red. My nucleophile attacks my carbon monoxide, just like we did before. The only problem in this case is that carbon can't have 5 bonds. And because it can't have 5 bonds, electrons go towards the oxygen. So it's a bit of a domino effect. And what you get is the following. You get a carbonyl compound. Now remember, this oxygen already has electrons, so when the electrons from the triple bond come over, we have 2 lone pairs. And I've got my acyl group. So anytime you have carbon monoxide, you will always be moving those electrons. Carbon can't have 5 bonds to it. Now let's talk about migratory insertion with alkenes. Oh, sorry. Now these are a little different than carbon monoxide. And so let me talk about these. And the reason for that is because this is an unsubstituted alkene. The reason for that is if you remember when alkenes complex to your metal, they don't complex through a carbon. They complex through the double bond, the pi bond. So if you go back to lecture 6, part 2, when we were talking about organometallics, the double bond is what's complexing to the metal, and it's a neutral ligand. Okay. Regardless of the fact that it's a neutral ligand, it's thought of as your electrophile. And just like before, your alkyl aryl vinyl groups are thought of as your nucleophiles. Okay. And so the insertion for alkenes is concerted, i.e., it's one step. Bonds are being formed as they're being broken. And broken at the same time. And so what I'll do is I'll draw the arrows in red so you can see how they insert. Now, this is our nucleophile. Attacks our carbon. Our carbon can have 5 bonds to it. Attacks our metal. And so what you get, if you follow your arrows, your metal is now bonded to a carbon. And specifically the top carbon. You now have your hydrogens and your R group. A couple of things that you should know before we move forward. Again, the R group can be a hydride source, an alkyl source, a vinyl source, or an aryl source, negatively charged. The other thing is that when the R group adds, not surprisingly, it adds syn, which makes sense because the metal and the R group are coming from the same face, so they should stay on the same face. So the addition is thought of as a syn addition. Okay, and we'll do examples of this in a second. The other thing is that the carbon that the metal adds to is known as the alpha carbon. So the carbon that's directly bonded to the metal is known as the alpha carbon, and it shouldn't come as a surprise that the hydrogens are alpha hydrogens. The carbon next door to the alpha, follow your Greek letters, is your beta. Oh, excuse me. So this must be my beta hydrogens. You do need to know that terminology. Carbon bonded to metal, alpha. Right next door is my beta carbon with its beta hydrogens. Okay, we'll be using that a lot. So let me show you an example of this. And we'll continue with unsubstituted alkenes, not just unsubstituted alkenes, but the addition of hydride sources. Okay. What I'll do is we'll do a quick electron count. This is palladium 2+, which means that there are D8 electrons for a total of, there's 2 triphenylphosphenes, 4 electrons, 1 halogen, 2 electrons, and 1 hydride source, 2 electrons, 16 electrons. This is an unsaturated system. So it has a vacant site for an alkene to coordinate. If it didn't have a vacant site, i.e., if it was an 18 electron system, a saturated system, this reaction wouldn't occur. Okay, but because it's only 16 electrons, my alkene can complex. So I've got my complex, and not just my complex that I from my starting material, but now I've got my alkene. And it shouldn't come as a surprise that this is an 18 electron count. So this is saturated. Nothing else can be added to the system. Okay. You can't bring in any more alkenes. If it does do any chemistry, it has to be all within the system because there's nothing else that you can add to this. Okay. Please make sure you know how to do the 18 electron count. It's still palladium 20, 8 electrons, right? 2 triphenylphosphenes, 4 electrons, 1 chloride, 2 electrons, 1 hydride source, 2 electrons. But now we've got our alkene that's neutral, 2 electrons, for a total of 18 electrons. So it's saturated. You can't add anything else. Again, everything that you do is occurring within the molecule. Now everything is intramolecular, okay? And just like before, I'll do the same thing. It does a migratory insertion. I'll draw my arrows in red so you can see the migratory insertion. Remember, nucleophile adds to carbon. Carbon can't have 5 bonds. Electrons go towards the palladium to form a bond, and what you get is the following. It adds syn. You have your syn addition. You have your alpha hydrogens and your beta hydrogens. Okay. The total electron count is back to 16 electrons. Feel free to calculate it yourself. Okay. It looks very similar to what we started with, palladium with a triphenylphosphine on the other side as well, a chlorine. But now instead of an H minus, we've got a C minus. So 16 electrons. So we're back to where we started. So again, you can't add anything to this. You can only do the chemistry within the molecule. Okay. Now let's do migratory insertion with alkynes. We'll go back to migratory insertion with alkenes, specifically substituted alkenes. I just want to make sure that I get through the carbon monoxide, alkenes, and alkynes. The beauty of it is that it's very similar to alkenes. And I'll use the exact same example that I did above, where I have my 16 electrons, and I'm adding my alkyne. Just like before, my alkyne complexes to my palladium. Now, despite the fact that there's a triple bond, the alkyne is only donating 2 electrons. So we're okay. We're at 18 electrons, just like before. I'll draw my migratory insertion arrows in red. It doesn't change. My nucleophile adds to my carbon. Electrons go towards the palladium. And now I've got a double bond instead of a single bond. Again, the carbon next door to the palladium or bonded to the palladium is my alpha carbon. Next door to that is my beta. Hydrogens are alpha if they're on the alpha carbon and beta if they are on the beta carbon. The nomenclature in the sense of how you label carbons and hydrogens is still the same. Okay. Now let's go back to migratory insertion of alkenes. Specifically substituted alkenes. And we'll continue to use the same example that we've used before. This R1. Just because I don't want you to confuse the substituents on the alkene and the substituent on the palladium. Okay. And so there's a couple of things that can happen. Part 2 is an alkyl group. Okay. There are two possible intermediates. For this reaction. And so what do I mean by that? And what I mean by that is that the alkene can complex to put the palladium in two different directions. And so let me draw both of those out. Okay. So the palladium can complex, or the alkene can complex to the palladium in two very different directions. And so why does this matter? And this matters because this sets the tone of how the nucleophile is going to add to the alkene. And so if this is my nucleophile, it adds to this carbon, and my electrons go and form a bond with the palladium. Please notice that my R1 is adding to the more substituted carbon, and it's the least substituted carbon that's bonding to my palladium. And so, of course, the product to this okay. Not surprisingly, this is still my alpha carbon and my beta carbon. But again, my R1 adds to the most substituted carbon. Okay. Now we can do the mechanism to the other possibility where the R1 adds to the least substituted carbon. And it's the most substituted carbon that forms a bond with palladium. And so if we take a look at that, Again, this is my alpha and beta carbon. My R1 adds to the least substituted carbon. Yeah. So those are my two possibilities. When do you use one over the other, or when is one favored over the other? Now, the R1 can add to the most substituted carbon when R1, my nucleophile, is a hydride source, which makes sense because H minus is the tiniest atom on the periodic table. It can add to the most substituted carbon. Now, R1 adds to the least substituted carbon when R1 is my nucleophile and I have alkyl or aryl or vinyl groups. And this is because of, not surprisingly, sterics. Okay. So when R1 is an alkyl group, it wants to add to the least substituted carbon. So when it's an alkyl, aryl, or a vinyl group, it wants to add to the least substituted carbon because of sterics, which makes sense, right? You're trying to avoid the crowding and you're trying to avoid any interactions with your R2 group, which also is an alkyl group, okay? So if R2 is an alkyl group, the only thing you can add to that substituted carbon are hydride sources, okay? There's more to these rules because all we've talked about are hydride sources and nucleophiles and R2 being alkyl groups. What if R2 was an electron withdrawing group and not an alkyl group? So if R2 was an electron withdrawing group, R1 would add to the least substituted carbon. Oh, excuse me. And this has nothing to do with sterics. This has to do because of electronics. So what do I mean by that? So take a look at the following example. Please notice that this carbon is the most electrophilic carbon. And what I mean by that is that when you draw resonance to the structure, your arrows go towards the oxygen. And because your arrows go towards the oxygen, this is the most electrophilic carbon. And as the most electrophilic carbon, that's where your nucleophile wants to attack. So it will always add to the least substituted carbon if your R group is an electron withdrawing group. Automatically. You've seen this before. This is known as 1,4 conjugate addition. You saw it in 124 at the end of the semester. So this is a 1,4 addition over a 1,2 addition. Okay? So when it's an electron withdrawing group, it wants to add to the least substituted carbon, not because of sterics, but because of electronics. Now, what if R2 is an electron donating group with lone pairs? Okay. So if you remember, electron donating groups can be ethers, amines. It doesn't have to be two substituents on the amine. It can be hydrogens on the amine. There's just lone pairs to it. Now, let me draw out my structure. Now, if my R2 is an electron donating group, my R1 adds to the most substituted carbon. Oh, let me draw this in red. Okay. Again, this has nothing, not because of sterics, clearly, but because of electronics. So sterically speaking, it looks like a bad idea, right? Why is R1 adding to this most substituted carbon? It makes absolutely no sense whatsoever. But it has nothing to do with sterics. If my electron donating group has lone pairs, okay? And it has everything to do with electronics. Why? If you look at your structure, and I'll redraw it for you. Please notice, I'm going to draw this in red, that you can donate your electrons into that carbon so that you can form a bond between the palladium and the least substituted carbon. And now you've provided an electrophilic center to attack. So it has nothing to do with sterics, but it has everything to do with electronics. You now have a pretty electrophilic carbon center so that you can go ahead and form your bond. Oh, between the nucleophile and the more substituted carbon. It's pretty clever. Please notice that no matter what in the migratory insertion, the insertion is always syn, whether you have an electron donating group, whether you have an electron withdrawing group, it is always syn. Let me draw out the product to this electron withdrawing group, which is probably what I should have done before. It is always syn addition. Migratory insertion is always, always, always syn addition. The carbon next door, well, the carbon bonded to the palladium is always alpha, and then of course beta, always. Whether R2 is an electron withdrawing group or an electron donating group. Okay. Okay. Reaction number 5 is beta hydride elimination. And this is just the reverse of migratory insertion. Okay. The mechanism is the complete opposite of migratory insertion. So the arrows are just backwards now. So what do I mean by all of that? Just like I mentioned, we talked about a couple of things, a couple of terms, the carbon next door to my, the carbon bonded to my metal is known as my alpha carbon, alpha hydrogens, and the carbon next door to that is known as my beta. Carbon and beta hydrogens. Okay. Now, migratory insertion requires that my metal have an open coordination site. Okay. So beta hydride elimination means just that. It's a hydride source on the beta carbon. So it's the beta hydrogen. For the elimination to occur, hydrogen must be syn to metal, which is exactly migratory insertion, right? Migratory insertion said hydrogen must be syn to my metal. Okay. It's a hydride source, which means it's coming with its own electrons, attacks the metal, and forms a double bond. Sorry. Okay. Please remember that migratory insertion was the complete opposite, right? Notice how the arrows are completely opposite. Migratory insertion. In this case, they were going counterclockwise, the arrows. In this case, they are going clockwise. Complete opposite. Okay? This is beta hydride elimination. Notice that the arrows start at the bond. It starts at the bond, not at the hydrogen, at the bond, because it's a hydride source that's attacking the metal. Okay. So for migratory insertion to occur, again, the hydrogen and the metal must be syn or cis in the product, which makes sense that the complete reverse, the hydrogen must be syn or cis to the metal. Okay? Okay. What if the hydrogen at the beta position isn't syn or cis? Okay? If your hydrogen is not if your hydrogen is not syn or cis, in order to do a beta hydride elimination, then what do? You must rotate about the carbon-carbon single bond. Let me write out single bond. Single bond to position the hydrogen on the beta carbon, cis to the metal. Okay? Which means that you have to see things three-dimensionally. Okay? So let's do an example of this situation. Sorry. Okay. So I've got the following molecule. I'm going to first label my alpha carbon and my beta carbon because I want to make sure that I'm deprotonating at the correct position. Please also notice that my substituent and my palladium are syn to each other. Okay? I need to do a beta hydride elimination. But I can't. And I can't do that because my CH3 group is syn. So what I need to do is I have to rotate about the carbon-carbon single bond and put one of those hydrogens in the syn position. Okay? And so what I do is you can decide which hydrogen you want in this case. In other examples, as we go through them, it'll be, there's a couple of more rules that we need to learn for each reaction. But in this case, I'll say, hey, I'm going to put hydrogen A syn. And so if I rotate, I'll draw out my palladium because that hasn't changed. If I rotate and my HA is now syn, that means that my hydrogen B is now wedged and my CH3 group is now dashed. Now I can go ahead and now I can do my beta hydride elimination. Again, I chose HA. In this case, you can choose HB. If you choose HB, that means that my CH3 group is going to be wedged and my HA is going to be dashed. Completely up to you in this case. Now I can do my beta hydride elimination. Again, it's the electrons that attack the palladium. I now have my palladium complex with the HA and my alkene. And I'm done. So when you don't have a hydrogen syn and instead you have an alkyl group, you have to rotate until one of your hydrogens is syn. Now, this was a pretty easy case because regardless of what hydrogen I added alpha, it didn't matter. My CH3 would be cis to a hydrogen. But if there are substituents on here, you always try to form the trans product, the trans alkene, okay? But we'll get to that as we're going through our reactions. Okay, one of the best examples of beta hydride eliminations is the use of Schwartz reagent. This is the Schwartz reagent, and you can treat it with really any alkene. And what I'm going to do is, let me number this alkene first. Okay. I'm going to draw the Schwartz reagent a couple of more times. Now I'm going to use a 6-carbon chain, but what I'll do is I'll move the alkene around the chain. And so in this case, my double bond is between 2 and 3, as opposed to 1 and 2. And then finally, I'll have it between 3 and 4. Okay. And so this is a really nice example of beta hydride elimination and migratory insertion with an alkene occurring. Okay. And so using Schwartz reagent, or Schwartz's reagent, regardless of where the alkene is on the chain, it gives you the same product. And that product is the following product. Notice that it's still a 6-carbon chain. It looks very similar to Schwartz's reagent, with, of course, the only difference, the hydride source. And so with whichever alkene you start, whether the alk double bond is in the middle, pretty close to the end, or at the end, you get the exact same product or intermediate, okay? And so what it shows is that the metal walks down the alkyl chain until it gets to the end. And it does it via beta hydride eliminations and migratory insertions. So instead of doing it for all three, because it's going to take me a while, I'll do the second example because it's somewhere in between the two and show you how it's walking down the chain. Okay. Because, well, maybe let me do the first one because this one's probably the most obvious, right? It's a hydride nucleophile. Example number 1. I use my Schwartz reagent and I complex my alkene where my double bond is at the end. It does a migratory insertion and I get the product. So I get the product. No big deal, it sounds like, right? It's fine as is. The other thing is I complex it usually at the top. You can complex it at the bottom, wherever you want it to be. But what I'm going to do now is show you example number 2. Okay, same thing. Okay, what I'll do is I'll do it this way too. It's the same molecule, right? I'm just drawing it. I'm just drawing it with the methyl group facing up. It's the same thing. Okay. The first thing that happens is excuse me. It's my double bond that has to complex. Okay. I apologize. It's my double bond that complexes to the zirconium. Just like before, it does a migratory insertion. So this was a migratory insertion. I'll draw out my arrows. Okay. You form your bond between carbon 2 and my zirconium. Carbon 3 now has a hydrogen. Five, 6. Notice how it's syn addition. Ooh. And now it does a beta hydride elimination. Now, here's the thing. You can do the beta hydride elimination with the hydrogen at carbon 3, but you would just get back to your starting material. There's a beta hydrogen on the other side, and you can do your beta hydride elimination with that hydrogen. And once you do your beta hydride elimination, your double bond is between carbon 1 and 2, which is exactly where it's at with the first starting material. So now I can do my beta hydride elimination. Oh, excuse me. So there's my beta hydride elimination. Plus, of course, the hydrogen that I formed. And then again, I do migratory insertion. And I get to my product. So in order to get to the product, I had to go through a migratory insertion, a beta hydride elimination, a migratory insertion. Whereas for the first starting material, I just had to do a migratory insertion. Okay. Not surprisingly, for starting material where the double bond is in the middle, you'll have a migratory insertion, a beta hydride elimination, a migratory insertion, beta hydride elimination, migratory insertion. And so it just keeps going, right? The longer the chain, the further in your double bond, the more beta hydrides and migratory insertions you have in order to walk the metal down the chain. Okay. Okay. But remember, anytime you do the migratory insertion, the substituent adds syn, and the beta hydride elimination, the hydrogen has to be syn to the metal. Okay. This is really these five reactions that I've taught you are really the very basics of reactions. They're like the SN2, SN1, E2, E1 of organic chemistry. Now what we're going to do is we're going to put them all together so that we can talk about the more popular reactions like the Heck, the Suzuki, the Stille, the Castor-Stevens. We're going to take all of these reactions and put them together, use some of them, and not use most of them so that we can talk about the rest of the reactions. Okay?